Okay. Hello. Good morning, everyone. Um, Welcome you all for another session of daily lead code practice. And today we have three questions, which are easy, medium, and medium. And let's start with the first question. Let me share my screen. Okay. Can you all see my screen?
Yes.
Oh, perfect. So this is a question of next creator element one. I think we have done the version of same question previously, so which is next creator element two, and this is the I suppose easy version of it. So we have given two arrays like nums one and nums two. What we have to do, so this is a sub array, you can say, of this bigger array, and we need to give the next greater element of the number from here in this. For example, if we want to find the next greater element of 4, so we 4 is over here, but there is no greater element after this 4, so we will give -1. When we go for 1, there is a next greater element which is 3, so we give 3, and next 2, and we don't have any next greater element of 2, so we give -1. So we need to give -1 if there is no greater element, and we need to give um, all the greater elements. We need to find all the greater elements of this subarray in this big array. Similarly, over this example, we need to find the next greater element of 2. So here is 3 after 2. And one thing is that there are distinct elements. There is no duplication. There is 3, and then 4 is not having any next greater element. So it's -1. Okay, any questions about this problem? Okay, any approach? Any brute force? Anything? Any thoughts?
My my approach would be find the next greater element in num2. So let ignore array num1 for now, and let process the num2. And let's say suppose we already find the next create an array for the next greater element, and then so I think that create a map. Probably create a map of next greater element for array num2. And when we have it, we just iterate through each element on num1 and retrieve the result.
Yeah, that's one approach. So, for example, we have, let me try the, so this is another example, another column. So we have this big array, and we need to iterate, you're saying this, and find the next greater element. So when we are iterating 1, so what data structure we need to use to see that the previous
we need to create a map. First, we need to create a map where the key is the value of the element.
Okay.
And the value of that map will be the next greater element.
So key is this element.
It's like 1, for example, right?
The value of the next greater element.
Yeah.
So, okay, so for that, I think stack would work best. So like when I when I start with 1, uh, and when I see there is a next greater element of the, when I see the top of the stack and see that there is a next greater element which is 3, so I'll give that, I'll give that to, I'll say one key 1 has an next greater element 3, like that, and put it in a map.
Yes.
And
then keep the 3 on the, pop 1 out from the stack and keep 3, push 3 on the stack.
okay, so now my stack is like, I see like I have pushed out 3 and 1, and now I have a stack of, now I have a 3 in the stack. So
Right.
next is 4, and 4 is also bigger than the 3. So I'll put like this and push, pop this 3 and put 4. Then I move forward. I saw 2. 2 is, there is no greater element of 2. I simply write 2 over here, and there is no key in this map because there is no greater element of 4 and 2.
Yes.
Correct?
So,
And
so
then,
now,
yeah.
Now just put 4, the key 4, and then the next greater element is -1.
Okay, so
put it to the map.
So I have to iterate nums1, which is the given one.
Yeah, but
And
in the map we need to put like the key equal 4 and then value equal -1.
so, or if we don't find the key in this map, then simply write a -1.
True. Yeah.
Yeah, we can see the map 1 has 3, we write 3, and when we see 2, there is no, so we write -1. Oh yeah, that works. Yeah. So anyone wants to go through with other example?
And on the stack, we not really put the value, push the value, we push the index of the array on it.
But we need the next, we need to see the elements, like which one. Actually, we have distinct elements, so I don't think so it will bother. Or
yeah, the reason we need to push the index of an array to it, because we can later access that index to assign the next greater element.
okay, yeah, that also works. Yeah, we can put the index and then go and find the, what was the value on that index. Yeah, that also works. Any questions, any doubts, any other approach? I was thinking about the brute force would be like, just search this 4 in the in this array, and then find the index of the 4 in this array, and then go through all the next elements of the nums2. That would be the brute force, and it would be more complex. Correct? So what would be the time complexity of this particular solution? So I'm thinking like we are iterating. It is for sure order of n, because order of n is like, n is the number of n is the number of elements of big array. So it is definitely order of n. And then we are also iterating this subarray. So it can be 2n, like we can say all the elements are present. They are both of equal size as well. So it can be go to 2n. And what's the space complexity?
So sorry, one thing. For the time complexity in nums2, for every element, we are looking through all the other elements to its right to find the next biggest one, right? So
Yes.
if let's say the nums2 is actually sorted in a descending order, like 100 to 1, then for the first number 100, we'll go through all the array till 1 at the end, and then find that it doesn't have a next biggest number. And we do the same for every element. So essentially it's n square.
But so actually we are just the approach which we did is like we just iterating this element and checking the stack top index and then comparing with the next element. So we are not coming back in this, I think. Yeah.
Yes. The n square is the brute force where you take the element in the first array and then figure out like where it is in the second array and then keep moving up until the last to figure out the element which is greater than. But the approach using a stack that we discussed, we are going through the nums2 only once. We are pre-processing it and storing the results in a map, and then once we have pre-processed the nums2, we will use the nums1 to figure out the next greater element by order of one lookup in the map. So pre-processing the nums2 using the stack approach is order of n, and then looking up is again order of n. So that's why it's order of 2n, and which is essentially like order of n.
Yeah.
Is the approach clear, like how we pre-process using the stack?
I think that's what I'm not clear of.
Oh, okay.
Okay.
Can we go with the second example?
Yes, yeah.
We can go with the second example. So let's say we have these 2 points and array.
Okay, so the first step is we will pre-process the nums2, okay, using a stack. Okay, so can you like just have a stack and make it empty?
Yeah, there is a stack.
Empty.
Yeah.
And then what's the first step? We will map, and then go ahead.
Yeah. So for example, we are in we start with the element and we are traversing nums2. We are at 1. We have 1. So we'll put in our stack the index of that 0. So which
or like, hey Sonia, like just put the number because it will be like easier.
Yeah.
Okay.
No.
We don't need to do additional lookup.
Yeah. So we put number over here, and when we are moving ahead for 2, we need to check first of all that if the stack is not empty, and then if there is any element in the stack which is lesser than that the next element which we have, so we'll simply pop it out and put 2. And similarly in the map we'll be putting the key as 1 and the value is 2. And similarly when we move ahead 3, we will see that 2 is lesser than 3, so we'll pop 2 and push 3 over here, and for here from in the map we can put like put what was the popped element and what was the next greater element of this, which is 3. And similarly when we move ahead we saw 4, we'll push 4, we'll pop 3 and push 4, and here we'll put 3 is 4.
So that's how like we are constructing the map. Can we take like one more example for num2? Let's take nums2 as.
Sorry, quick question. So does this mean the stack always has maximum 1 element?
No. Like, let's take a second, like one more example. Okay. Yeah, take it 4, 3, 2, 1. No, like remove the 1.
Okay, 4, 3, 2, 1. Got it.
4, 3, 2, 1, and then 5.
Okay.
Okay. So for each element, if you take a look in the nums2, what's the next greater element for 4?
Yep, 5.
Same for 3, 2, and 1.
Yeah.
Yeah.
Okay.
So we'll do the while loop until unless our stack is empty and we have a next greater element.
Yeah. So you put like 4 first.
Yes.
Okay. Then because a stack is empty, there is like nothing to process. Okay. When we start, so we put the first element in the stack. Then we go to 3. We like don't put it in the stack right now. Okay. So when we go to the 3, we peek at the top of the stack. Okay. The element at the top is greater than the current element. So in that case, we put the current element onto the stack. 3. Yeah. Can you put like 3 in the stack?
Yeah.
And then again, like go to the next element, which is 2, peek the stack, which is 3. Okay, which is greater than the current element. So we will put the current element as 2. As 2. Same thing for 1. Now, when we reach 5, okay, and we start like peeking the stack, 1 is less than 5. So we definitely know that the greater element to the 1 is 5, right?
Mm-hmm.
So we pop 1 and make an entry in the map.
So we will
So
not right now.
little confused on that. Like, I have a question. Like, we decided like when there is a greater element, we have to pop and then put that greater element in the stack, right? So we have to pop 4, 3, 2, 1 every element and then keep a 5.
No, like we.
Yeah, actually, we need to like until unless all the elements, for example, we just need to which we just create that in a map like this, and then we next is then again we see 2. Yes, it's lesser than until unless this whole stack is the elements are lesser than the next 5. So we'll keep on popping it, and then if it is, if for example, if there was a 6 over here, so we'll stop over here, will not and then put 5 over here. Rest will be just popped out like this.
So,
And that will go in hash map, right? Whenever
yes.
we are popping. Okay.
Yes.
Element which we are popped, we are creating a key of that element, and the value would be the 5 because the greater element was 5.
Yeah, we keep putting the numbers in the stack since we haven't find any greater element. Okay, and once we find any greater element um, and compare it with the stack top, if the element in the hand is greater than what is on the top of the stack, we know like we have a solution for that element on the top of the stack, and then we keep popping from top of the stack until the current element in hand is greater than the top. So in this case, like when we put 4, 3, 2, 1, and we got 5. So 5 is greater than 1. Then again 2, which is on the top, and then 3, which is on the top, and then 4, which is on the top. And we keep like making the entries in the map: 2, 5, 3, 5, and then 4, 5.
Yep.
4, 5, and then like we remove 3 from the stack, 4 from the stack, and then now the stack is empty. Okay, we can put 5, but we don't have any greater number after that, and like after 5 we don't have any number. So that's the map that we have constructed.
And if you if you you see, we see that anytime you have item on the stack always maintain in the decreasing order. So you know, in this case, you will, if we process, we will see that anytime, you know, element on stack on decreasing order, and this is called a monotonic stack.
Makes sense.
Actually, we did the same problem. That's why Roger also mentioned that Kuneet did the question of, we did the duplication of one array to see the next element, right?
Yes. So look at the Mondays video on YouTube.
Yeah.
Okay, we like Tuesdays, whatever like we discussed on Tuesday for the Mondays questions. it's a kind of like similar interesting problem, but that problem is a medium.
Yes. Yeah, that was a medium. And how we have solved that. That's also an interesting approach.
So I hope like this is clear, and that's why the complexity is order of n. Maybe like we can move to the second problem soon.
Yeah. Any questions?
No, thanks.
Okay. Let's move ahead. Okay. We have a next problem which is from a hard bucket, and we need to find the power. We need to implement the power xn function. Like for example, 2 raised to power 3 is 8. So we need to implement this function, and we know everybody knows that there is a library of power xn function, but we don't need to use that obviously because this question is about power x upon n, x raised to power n. So we need to implement this function. And for example, there is 2 and x is this 2 and raised n is this 10. So we need to go for x raised to power n, which is 2 raised to power 10 is 1024. And make sure that we have a negative numbers as well, which is like 2 raised to power minus 2. So and everybody knows the explanation of this, minus 2 and then 1 upon 4 is 0.25. So this is an answer. Okay, so how will you solve this question? Any thoughts? Anyone? So what would be the brute force, how you implement this? Like how would you start going multiplying 2 and 2 until unless you reach 10, and that's an answer, correct?
And multiply 2 3 times.
Yeah.
For loop.
In a for loop, you'll multiply n times, and that's an answer. But that will be time complex, and I'm sure it will reach to TLE over here in lead code.
But let's say, if we do that, can we write down if we do that and then see if we can optimize based on the brute force?
So we'll multiply x like n times. That would be an answer.
Yeah, but like I think with yeah.
Just
for example, if x equal 5, I mean n equal 5, so we multiply x by time x can 5 times.
Yeah, so it will be like whatever x, it will be, for example, in a while loop, and what will be whatever the new x was there, that will be like your answer is multiplying x again and again. Sorry.
Can we write like let's say we multiply a 5 times, a times a times a times a 5 times.
Yep.
Yes. So this is a brute force we do, right? And then see we can see. Yeah.
One more thing, like multiplication can be represented as sum of the elements. Like if it is a raised to 5 means oh, this is exponential. No. I will take my words back. Let me think again.
Yeah. So yeah, it is like multiplying same number again and again.
What about like negative numbers? Let's say if we have to the power minus 3.
So that can be covered, like if there is a number like this 2 raised to power something like that.
Let's say take 2 to the power minus 3.
Yeah, like for example, we have 2 raised to power minus 3. Then it is like we can do if there is we know that in the starting only if n is negative, then we can replace our for example x is equal to 1 by x. For example, this was our x, so we can replace if n is negative, we can replace x is equal to 1 by x and then solve new x, whatever the x we have created, and solve this.
Yeah, so any number to the power minus 3 can be represented as 1 by that number.
Yes.
To the power 3, like 3. Okay.
Yeah, so it will be like
that's a simple maths.
Yeah, so it would be like now 1 by 2, and now we will be having, we need to do exponential of this raised to power using 3.
Yeah, so our n will convert from minus 3 to 3.
Yeah.
Yeah, or we can look at, we can take note of it. I mean, if with the power to negative 3, then we make it become positive, and then when we get result, and we just put 1 over whatever the result.
Yeah, that's also one, or you can do at the end, or you can do in the starting. So whatever works for anyone. But the main problem is how to reduce your complexity of multiplying, because I have solved this question, I have followed this approach, my answer went to TLE. So what's the other approach?
So let's say if we look at line number 9, right? We see that A, being multiplied multiple times, then we see that instead of multiply multiple times, we can divide it into 2 groups, and in this case, let's say the first 2A in one group.
Okay. And then
the last 2A will be in the second group.
Okay. So you are saying whatever the we have n, we should divide it by 2 and then solve each group separately. Something like that?
Yes. But then if we look at this in this way, we see if we solve group 1, then we already partially solve group 2. Because yeah.
So half of it will be the same, whatever the group 1 was, that answer. For example, this was A into A. So this A into A should belong to group 1. It's like group 1 into A. It should be like group 1 into A now.
Right.
Correct?
Yes.
Yes. So something, this is, I'm understanding the approach, like we need to use something which is already computed to move ahead and solve the next one. And if I can see, this is an even number and this is an odd. So which means to solve the even, no. So we have something like this, which is an odd multiple, and we can divide it by 2, and if our n is something which is even, then this would be solved like a normal computation. Otherwise, whatever the answer was, that we can use and multiply with that A to find the next greater element. Is what you are trying to say? Anyone?
Yeah, that makes a lot of sense. It's almost like if you have this a times a times a times a written a bunch of times, right? We're essentially trying to fold it onto itself. So it's almost like we're traversing it log n times.
So if I can, yeah, come up with a formula, it is like if we have n is even, if n is even, we are doing, we are dividing n by 2, and we are dividing n by 2 and doing the computation of whatever it was left. For example, that function is x comma n by 2, and this would be whatever the answer. It's, let's say it's anything which is y. Then we need now our, for let's say if our, this is for even, and if it is an odd, we need to use whatever the y we have created, and we'll call again function x comma, now I don't know, it should be n by 2.
Hey Sonia, like, so in case of even, the result should be y into y. Okay, because that's what like we will return.
Oh yeah, so because we have already created a group 1, so it should be group 1 into group 1, correct?
Yeah, y should y multiply by y, and in case of if n is odd, then whatever n by 2 like we are going to get. Okay, yeah, you write like n by 2, y equal n by
y equal n by 2.
Function, the same thing that you have written above.
Okay, so it should be like
Yes,
this.
whatever whatever like we get, and then it should be y into y into y into x.
Okay, yeah.
Because doing like n by 2 will make it even, so it should be the same, y into y, and then we have like one left, so we will multiply.
Okay, that makes sense. So but my question is, if there is already we have computed y, we can't use this y into over here?
Yes, like yeah, we can do that, because how you will write this program, like when you are writing it, okay, you will do y equal to function x n by 2.
Yeah, and then just
then check whether if your n is even, return y into y. If your n is odd, return y into x.
2x. Okay.
Yeah. And how to check even and odd, like just do the mod by 2 and then see if the result is 0 or not.
Yeah, we can do that. Like if n of
and
odd is equal to 0, run this.
And we are trying to do recursion here. So what should be the base condition?
Yeah, so what would be the base condition? So if n is 0.
Yep, because we are dividing n by 2 every time. So eventually like n will become 0.
Yeah. And we need to return.
What is number the power 0?
1.
Yep.
So we need to return 1. That would be the base case.
Yep.
So yeah, this approach would work. Any question?
Sorry, I thought I have the same thing. I can do it in an easier way. We can take the advantage of shifting the numbers. Like in generally binary representation, if we right shift a number, that doubles the number, and if we left shift a number, then that do half that number.
Yep, that's the other way around.
Yeah, so we can use that, and every time we shift the x to the right and shift left of n, we do that, and whenever we get an odd, that means like we get an 1 in LSB. We can add an extra x, multiply to that value, and do until n is 0.
Yep, that makes sense, because what you're trying to do, you're trying to divide, instead of like dividing by 2, you are trying to right shift it so that
Yeah.
Yeah. So it's like by 2 means we are going for a right shift, and modulus 2 means we are what we were doing.
So
But
the only
So
problem
can you
I
I
see
don't
that is
think the shifting will actually work in the case of double or float, because the representation of double and float is different than what is for the integers.
exactly.
So yeah, that also is the what Aditya is also saying, mentioning it. It is also very it is also very optimized approach.
But help me understand, like we are shifting only n, which is integer. We are not shifting x. So the goal here is to try to figure out like what should be the next n value. In the example which is written here, we are doing n by 2. So we are right shifting to reduce the n. We are doing nothing with the x.
We'll be doing with the x because
So
we are
we will multiply it, but like we are calculating the value by shifting. Like was that the suggestion?
Yeah, actually I thought of right shifting the x also, but it's a decimal, so we can go with multiplying it by itself.
Yep, because we cannot like shift that.
So yeah, so we can multiply the x and left shift the n and go on like that.
so, but the problem is that we will be reaching we'll be reducing our n very early. So I think we need to save some answer somewhere. Like if, for example, if we have reached to the odd number, we need to save that answer.
Yeah, so that's why we need to check LSB every time. If it is LSB, then we multiply an extra f, like we multiply an extra x every time. So every odd number we are multiplying once extra. Other than squaring it, we are cubing it. So
Yeah. So for for your approach is like n is if n is odd,
yeah, we cube it.
you'll cube it.
If it is even, then we square it.
Okay. If n is even, we'll square, and we'll
and keep
do
shifting.
like something like that.
Yeah.
Okay. And when we'll so whatever the new x will be there, we'll just multiplying it.
Yeah, you're multiplying it and putting it in the same value. So like we don't need an extra variable or something.
Okay. Yeah, that's also an optimized approach.
Thank you.
So did you try this problem? Like this approach, did you try this approach?
No, I didn't solve it, but I solved the same thing under integer values, but this problem I didn't solve it.
Okay. So anyone else have solved this problem and with the solution? Yeah. I think Aditya sent a message that he, yeah.
Are you looking for the code?
Yeah, so I'm asking about the code. But
yeah, me too. I want to see it.
Yeah, I can show the code, like if you guys are interested.
yeah, sure. I'll stop sharing.
Code is like exactly like what we just discussed. If you see, so this is the function like which calculates the number like to the power, and on the top, like we are just trying to normalize it. Like if n is negative,
Yeah.
okay, we do n equal to minus n and x equal to 1 by x, okay, to make it consistent. And then it's the same recursive function. Base case with if n equal to 0, return 1, cause any number power 0 is 1.
Is 1, correct.
Okay. Then you get the half of that number by doing the power.
Recursion, yes.
Okay, like using the recursion, and in that recursion, like pass n by 2. Okay. And then if n by n mod 2 is 0, then you have to return half into half. Okay, because that's how you double the number. So in this statement, x will be raised to power of n by 2. So to raise the x to the power n, we have to multiply the number by itself. Okay, do the square of that number. And if n is odd, then half into half and x like one more time. That's it. Okay, so if it is to the power 10, we will get 1024.
Yeah, that's the approach which we discussed. Yeah, thank you. Any doubts? Thank you, Gaurav.
What should be the time complexity?
It will be, actually n is reducing exponentially.
By half.
Yeah, by half.
Log n.
Log to the base 2.
Log n. Yep.
Log n, correct. So, thank you. Any other question or doubts? Okay, we'll move ahead with our last question. Okay, let me share my screen. Okay, can you all see the question?
Yep.
Okay, so we need to construct the complete binary tree in which every level except the last is completely filled and all the nodes are as left as possible. I hope everyone knows about what is complete binary tree. So what complete binary tree is, for example, you have 1 and on the left side you will be having 2, on the right side you will be having 3, and on the last level you can just have 1. For example, if you have 1 and every other elements are empty, the children's are empty, so as far as left you can fill, that's an answer. This is a complete binary tree. I think so yeah, we need to implement this complete binary tree. So what we'll be providing, what we have to do is we need to write a data structure which is initialized with a complete binary tree, and the operations which we need to do is insert. Like first of all, we'll call this our inserter, which will be having root, which will be providing us the root, and this will be the head of the tree. And whatever the new elements which are inserting, dot insert function will do. Whatever the new elements are coming, we need to insert it at a particular position, and we need to return its parent value. For example, in this case, if we insert 4, we need to return 2 as a parent of the inserted node. And in get root, we'll need to return the root which was provided, because that would be the head of the root. For example, let's go with example 1. So this is called this function is called with root as 1. So it is 1. Now insert is called with value 2. So now its parent is 1. So its parent is 1. So it returned 1. And when they call the get root function, they simply give all the they return head of the root, with head of the tree, which is 1, and rest is like everything can build upon the head of the root. So this was an interesting example. So what they did, they provide this as root. So which means that this is already implemented 1, 2, 3, 4, 5, 6. And then they insert 7, and wherever 7 is inserted, let's say 1, 2, 3, 4, 5, 6 would be here, then 7. So next we have a tree like something like this, and we need to insert 7. Obviously the 7's right is empty, so we need to fill that first. So when we inserted 7, we know that its parent value is 3, so we give answer 3. And next, when insert is called with another value as 8, we need to fill as far as possible. So the next element where it needs to be placed is the child of 4, like over here 8, and its parent is 4. So we need to return 4. So this is the answer of 4. And when they call the root, like get root, so all the elements, which is 1, 2, 3, 4, 5, 6, 7, 8, all the nodes are returned. You can say that you can return just ahead of the root and everything would be returned. So yeah, we need to build this tree with the data structure, what we need to use, and yeah, we need to do this. Any problem in understanding the question, like want to go for more example or explanation, I can go, and if it is okay, then we can think about the approaches or the data structure which we need to use to implement this.
Yep. Also, I want to ask, like, hope everyone is clear what's a complete binary tree.
Yeah, if any doubt about the complete binary tree is, I think they are good. So what would be the approach? How we can solve this?
So I think since this is a complete binary tree, the easiest thing is you cannot fill a right node before you fill the left node of any given root, of any given node, right? Left
Yes.
child is filled and then the right child is filled.
Yes.
So basically, if you store it in an array, you cannot have any gaps in there. So that would mean any inserts are just appends to the array. And then since it's a complete binary tree, parent is always index over 2.
Parent is always index over 2 means?
So here in the tree, we have 1, 2, 3, 4, 5, 6, 7, right? In the example, the one you wrote.
Yes.
So if you take 2 example, for example, then it's an index 1, right? 0th element is 1 and first element is 2. Then the positions of both of its children will be 2k and 2k plus 1.
Yeah, that's one thing. So
are you like trying to store the results like in an array or something like that?
I think it's, I might be wrong, but it seems like the whole thing is pretty much an array. Initially, whatever inputs they give, it's like a full array. And anytime an insert happens, we just add that element to the end of the array. And get root will return the whole array. And then for the insert, when we need to return the parent element.
So just to be clear, okay, the output like which is shown, it looks like an array, okay, but like let's take a look at the class which is given as CBT inserter. You are given already a complete tree. Okay, you are not given like a single root, you are given a tree.
Yeah.
Okay, that tree can be in any state. In the first example, there is only like one node in the tree, which is root, and value is 1. In the second example, you are given a tree with the six nodes. Okay, and then the root is 1. And every time you are inserting, you have to insert it in a binary tree. Okay, you are not inserting it in an array, because once like the get root is called, simply you have to return the root, whatever is passed in. Okay, you have to return the root, but when you try to print that root, like, or traverse that root, it should be a complete binary tree, and then the output should be like 1 2 3 4 up to 8, like whatever it is. So it looks like an array, but like for the example that they have like given us, but it's a tree.
So,
got it.
Yeah.
So what we can do is we can like use this root and fill our array first. Like whatever, if we have taken a data structure, we can traverse this root and put that in an array.
Okay, what will happen? Let's say you are given 1 2 3 4 5 6. Okay, like take the second example. Okay, where you are given a root,
Yes.
tree root. Okay, you are given a tree as 1 2 3 4 5 6. Okay,
Yes.
what you will do with that tree?
So this will be our first index 1, which is like in a binary tree. How we will be using like parent is this
1,
and its left children is 2 into parents index.
no, like
Right.
tree doesn't have any concepts of indexing. Okay, so what is given to you is a root. Okay, you are given a root of a tree. You are not given any array.
Yeah, it's not given an array, but I'm
Yes.
just thinking that how we can.
So let's like remove those. Just draw a tree. Whatever you have like at the bottom, just remove 8 and 7 from it.
Yeah.
Okay. So this is the tree which is given to you, and you are given the root, the pointer to 1. Okay. Now what will you do with this root?
Hello, am I audible?
Yes.
Okay, so Tanmay this side. Basically, it's what I think is it's simple level order traversal. We're having 3 approaches for that. We could use any one and do a simple level order traversal. And then we'll fill, whenever we'll reach the last place, we'll fill the next position.
Okay, so we will do the level order traversal, and where we are going to like store the results.
It's a list of lists, right? So I guess there's no issue in storing the results. Like for example, when we're required to insert, I'll directly add it to my tree, and I'll create a tree binary tree data structure.
So binary tree data structure is given to you, which is already given as a root. Okay. Now, let's say in this example, I called insert with 7.
Okay.
Okay. What you will do?
I'll do the level order traversal.
Okay. And, so the level order traversal to like put the new to do the insertion.
Yeah.
Yeah, which is correct, because like you traverse 1, okay, and then see 1 has a left child which is 2, and which is already full, because it has both left and right child, and then you go to 3. Okay, then you see like it has a left child, but it doesn't has a right child. So maybe that's the correct place to insert 7, right?
Yeah, basically what I'll do is I won't do it this much. I'll directly go to 1 2 3 4 5 6, and then I'm at the last position. So I basically know that I'm having on the position where I need to like add my object like 7.
Yeah, because here like if you go to 6, okay, you lost track of 3. That 7 need to go to the right of 3.
Yeah,
it has nothing to do with 6.
Yeah.
So how you will be returning the parent node? Like we need to return 3.
Yes. So where the 7 should go? 7 should go to the right of
3.
Okay, which is, so we don't need to traverse up until 6.
Yeah. Sure.
Okay, we can just traverse up until 3 and then see, okay, 3 doesn't have a right child.
Yes.
So that's the right place to insert, and then okay, can you add 7 there?
Yeah, so now we'll be adding 7 over here.
Okay, now what if the insert is called again with 8?
So now basically I'm having my level, right? Here I got that my level is filled up to 3. So now my level will get plus plus, And as I know that my level is incremented, I know the position where it has to be inserted. Basically, it's how you write the code and manage the stuffs.
So what's the data structure in which you are managing the levels?
Simple binary tree using the level order traversal. For each call, I'll be having my level. For example, I'll call 1 with 0 level, 2 and 3 with level 1, and then 4, 5, 6, 7 with level 2. But when I'm over with 7, I know that the level I have to go to is 3. So I'll do 3.
Okay. So how will you figure out like 4 here? Because it should go on to the left of 4.
My call is working as just a minute. From 1, I called for 2 and 3. Then I know my level is 2, and I know that this level is full. So I called for 2. I'm having both the childs, my level 4 and 5. Then for 3, I called 6 and 7, and I know that the level is full. Now I'll call from 4, and I'll see that there's no child. So basically, I'll get the child or that I got the position.
Okay, makes sense. So for every insert, you are traversing the tree from root to wherever it need to be inserted. Correct?
Yeah, or okay.
Can we optimize it?
Containing a previous, I guess. Let me think. Just a sec.
Yes, Sonia, like, can I share my screen?
Sure, I will stop it. Sure.
Okay, so this was the example that we have taken. Okay. Okay, so 7 will go onto the right?
Yes.
Right of 3. So the approach which was told was correct, because every time a insert is called, okay, we already have a route which was passed to us in the constructor. Okay, we have a route. We will start traversing level by level and then see. So we start with 1. Okay, we will see that, okay, left is full, left is there, right is here, right is there. So 1 is not a candidate. We go for 2. Next, in the level order, we see 4 is there, 5 is there. So like left is there, right is there. So 2 is not a candidate. Then we jump to 3. We see 6 is there, which is the left, right is not there. So we got a candidate where we can insert onto the right of 3. Correct? Okay. Again, we get another number, which is 8. We will repeat. We will start from 1. Has a left and right child, it is full. 2 has a left and right child. 3 has a left and right child. Then doing the level order, we will reach 4. 4 doesn't have a left child, so 4 is a candidate.
So one more thing, like it is a complete binary tree. So how many nodes on the each level? We know it. We can calculate, right?
But you have to traverse the tree like fully.
No, I don't need to traverse. Like I know that it is going to the next level because it is complete binary tree. Then I know level means if we are while traversing itself, we are taking care of the levels. Then we know that it is going to the new to the next level.
So for example, over here, 2 raised to power, we reach to the level 3, and 2 raised to power 3 is.
So let's say the tree is like in this position right now, and I have to insert 10. What you will do?
Oh no, I was talking about 8. 8 is going to the always to be left of the leftmost child in the tree.
Yeah, okay. Like we filled 8, we filled 9. Now we have to fill 10. What should we do?
Yeah, then I have to go to the traversing from 1 to again. Yes.
We need to have the location like parent should be 5 where we are locating.
Yes. Okay. So essentially, like we already talked about one approach where we start from the root and then we figure out doing the level or order traversal that what should be the correct position to insert, and then we simply insert it. Okay. Now the question is, how can we optimize it? Okay. Same approach, let's say, and how do we do level order traversal? Using a
BFS.
BFS queue. Correct?
Yeah.
Okay. Start processing the elements. Put one in the queue, right? Okay. This is like how you initialize the queue. In the second step, peak one, like look at the element which is onto the top, like in the front of the queue. What's the element in the front of the queue? 1. Does 1 is full? 1 we can just check, okay, 1 has a left or 1 and 1 has a right, correct?
So yeah, it's
so we will put 1, 2 and 3 in the queue and we simply pop off 1. Right? Because 1 is already full, we don't need 1.
Yes.
Then again peak. In the third step, like we will again peak the queue. What's the top like front element in the queue?
2, and we'll pop.
The front element is 2.
Yes.
Okay. So for 2, we will first add the 2's children, which is 4 and 5. Okay. Now is this 2 full? Already full?
Yes.
Okay. So remove it from the queue. Okay. If it is already like full, we can remove it simply. Now this is the state of the queue. What's the next element?
3.
3. Is 3 full?
3
No.
is no.
No.
Okay. So we will break from the constructor. Okay. So this is the state of the queue while the constructor was called. Okay. We will just maintain this extra queue, and also for sure, like we have to save the root. Okay. Just have a variable called root in which you will save the root which is given to you. Correct? Now, let's say now insert is called with 7. What should we do?
So what I am thinking, where you have saved obviously the 3 was the last one which was not completely filled.
Yes.
What we need to do is we need to pop the DQ that and insert the new element over there.
Peak, don't pop.
Yeah, peak.
Okay, peak. What you will get? 3.
I'll get 3. Yeah.
Okay. We know like it is in the queue because it is not full. Okay. Check left.
Yeah.
Check right. Okay. Is left null?
No.
Okay. Is right null?
Yes.
Okay. So can we like simply insert on the right of 3?
Yes.
Yes?
Yeah.
So what should be, like when we insert to the right of the 3, we also put that in the queue.
Queue. Correct.
Okay. So sorry, it was.
You inserted 6 left first and then.
Yeah,
right.
6 we already inserted.
Yeah, insert 6 there, yeah. 3, 4, 5, 6, yeah.
3, 4, 5, 6, yes.
And then we inserted 7. And then after the inserting, we return
3.
Okay. Now in the same operation, when we are inserting, since we just peaked, okay, we already have a reference to 3. We will check. Now it is full, so we will remove it.
Yeah. As soon as you have the node's right is filled, you need to remove it.
Yep. Okay. Yep. So you remove it, and then your 7 is now at this location, correct?
Yes.
Now when we will get 8, what should happen? Repeat the same thing. You get now 8.
Now we peek 4.
Peek 4.
And insert it in the left because left is null.
Insert on left because left is null.
Null.
Okay. And then in the queue,
return 4. Oh no, still, yeah.
7, 8. So that was the state of the queue. Like we will put the 8 in the queue.
Yes.
Okay. Now check. 4 has left, has right. It doesn't have a right.
Yes.
Okay. So we will leave it.
Yeah, will not remove it.
Okay. So your 8 will go at this location. Now, what about 9?
So we'll check in a queue that which was 4 and 4 left, we peek 4 and 4's left is and we need to check 4 left. It is there, 4 left is not null. Then we move ahead and check and go for 4 right.
Insert on right.
Yes, insert on right.
Your queue will become 9 here.
Yes.
Okay. Again check. 4 has left, 4 has right.
Yes.
Okay. So remove it from the queue.
Yeah.
Okay. And 9 is now here. So that's the operation like we can follow.
Yes, that's the approach we should.
Okay. So the solution which was suggested, like to use a queue, do the level order traversal, okay, was right. But like we can just optimize it by maintaining a queue, and the front element of the queue will always be the element which is a valid candidate to insert a new node, which can act as a parent. Now the only thing we have to do, we have to check whether we have to insert it onto the left or insert it onto the right. So it's like a simple if check.
Yes.
And then once you insert it, again check whether if it is already full, then remove it from the queue.
So I was thinking like to more optimize it, why we need to check every time if left has left or right, because if the left is null, it will be put it into the left. Otherwise, it will go to the right, and the node has already reached to the right. So we just need to remove from that.
Yeah. It depends like how you want to implement it. Okay.
Yes.
So just looking at the solution, I have these two private variables. I've taken a root because I want to store the root, and a queue. Okay. And then get root will always return whatever the root is passed to me. Correct? Now the queue is initialized, and while true, I will do the label order traversal.
Yes.
Okay. I first insert like the root, and then check if the left is not null for that element. Add left into the queue. If right is not null, add right into the queue. Okay. And then if left not null and right not null, okay, simply pull from the queue. Otherwise break. Okay, because in this scenario we will go from 1 to 3. Okay, and then we will poll 1, poll 2. So this will be the state of the queue while this constructor will finish. And then in the insert operation, peek, as we talked about, look at if the left is null, insert the node into the left. Okay, else insert the node into the right. Add node, whatever the new node that we have created into the queue. And then if the left and right are not null, then pull from the queue, because that number, like whatever the node is in the front of the queue, we cannot insert any more to it. Okay. And yes, like as you said, Sonia, like we can optimize it, but just to keep it simple, I implemented this way.
I have one question in your code. Can you go in the yeah? So so you are creating a queue where like peeking that queue. So how, like, if the items left, for example, 3 doesn't have left and right. First of all, if it is not, okay, so you're doing opposite of it. Got it. Actually, I was checking the, if it is left is null or right is null, then put that item. You're doing opposite. Got it.
Because if you have a left, you just put it. If you have a right, you just put it.
Yeah.
And then when you check, like if the current node that you are processing on that label has both left and right childs, then you pull it from the queue.
Yeah.
Or you don't need it anymore.
Yes.
Okay.
So you could have used DQ there, right? If you just want the left guy, you don't have to traverse all the way. Is that right?
I didn't got it.
So DQ, like double-ended queue, where you can insert and peek from both sides?
Yeah.
Here I don't need to like peek from both sides. I just need to peek it from the left, which is like the front of the queue.
Okay. So
why I need to like peek from the both end?
Okay, so this one actually I was looking into this I think constructor code. I thought you were doing it again and again. Here in, like, you know, where you are going to line number 30.
Yeah.
And there is a like while block, while true.
Yes.
So this is just one time you do, right?
Yes.
Okay.
This is, I'm doing the pre-processing in the constructor. Okay. So so in the second example, while the input was 1 2 3 4 5 6. Okay. So this was the queue which was given to me. Okay. I pre-process it, remove 1 from the queue, remove 2 from the queue, and then keep 3 as the first element in the queue. So this is my state of the queue, which is highlighted on line number 80. While the constructor is done.
Okay. Yeah, looks good to me.
Okay. Now, what's the time complexity of this operation?
So the only operation which we did is like first, the operation which first we did is we implemented the queue.
So let's talk about like time complexity of the insert operation. Let's say like we already pre-processed the queue, we have everything. What's the time complexity of the insert operation?
It's only O of 1.
Yes, right. And time complexity of the constructor, it's the number of nodes that we are given in the root.
Right.
Okay, so that's how like we can optimize the insert operation to be order of 1. Any other questions?
No, I think this is good.
Thank you.
Yeah, thanks, Sonia. Thanks, Gaurav.
Yeah.
Thanks, Gaurav. Thanks, Sonia. Yeah, thank you.
Nice.
And thank you, everyone. Do you have any questions or anything anyone wants to discuss about any other solution or something? Okay, I'll stop the recording.